This video covers Stat 454, Chapter 4, Section 2, Preview of the Simplex Method. We're going to begin attempting to solve an LP with the simplex method by looking at this LP, maximize z subject equal to 4x1 plus 3x2, subject to x1 plus x2 less than or equal to 40, 2x1 plus x2 less than or equal to 60, along with the sign constraints x1 and x2 greater than or equal to 0. We learned last time that in order to solve this LP using the simplex method, we have to find the standard form of the LP. Since these are two less than or equal to constraints, I will introduce two slack variables, S1 and S2. That turns the LP into maximize z equal to 4x1 plus 3x2, subject to the constraints x1 plus x2 plus s1 equal to 40, and 2x1 plus x2 plus s2 equal to 60. Now, if we think back to Chapter 3 material, we learned that the solution to an LP has to happen at one of these corner points. These corner points are solutions to the system of constraint equations. So we need to try to find some way to find a solution to this system. There's a problem though. There are two equations and four unknowns. It's common knowledge that in order to solve a system of linear equations, you need to have the same amount of unknowns as equations. So how do we go about finding this solution? The technique is the technique of the non-basic variable. And it's so easy. Pick a number of variables and set them equal to 0 so that the system becomes solvable. The ones you set equal to 0 get called the non-basic variables, the NBVs. The others become the basic variables, the BVs. So let's take a look at this system. You can pick any two of the variables that you want out of x1, x2, s1, and s2, but you will learn in practice that the slack and excess variables are usually the ones you want to start with first. So I choose to set s1 and s2 equal to 0 as the non-basic variables. That creates a system of equations that looks like this. x1 plus x2 equals 40, and 2x1 plus x2 equals 60. Now I am free to use the regular technique of solving systems of linear equations in order to find these other two values. I think on this one in particular, I'm going to subtract one equation from another. By doing this particular subtraction, I'll cancel x2 and be able to find x1. So x1 minus 2x1s is minus x1, x2 and x2 cancel. 40 minus 60 is minus 20, creating x1 equals 20 as one of the other values. Don't forget to back substitute to find the other. That creates x2 equals 20. So this thing that I have just created, x1 equals 20, x2 equals 20, s1 equals 0, and s2 equals 0, is a thing called a BFS, a basic feasible solution. And what the simplex method does is it takes basic feasible solutions and uses them to generate more optimal basic feasible solutions. So we'll get an initial solution, we'll transform it into a new solution, we'll transform it into a new solution, and after we go through that process a particular amount of times, we are going to have a guaranteed optimal solution. There are a few ways of writing basic feasible solutions. Obviously, the way I just wrote one here. Sometimes we write them as vectors. I tend to like column vectors, like this. Sometimes you write them as ordered tuples, like this. This, this. All three of these things are the same. You can do this process of finding a basic feasible solution for every pair of 0 non-basic variables. So for example, I could come in and say, I want to do the same process, but with non-basic variables, x1 equals 0 and s2 equals 0. That creates a system that looks like x2 plus s1 equals 40 and x2 equals 60. Turns out we already have one solution. If I back substitute, I end up with s1 equals negative 20. And listing my solution, I would have one of the form 0, 60, minus 20, and 0. You might be tempted to say this is a basic feasible solution, but that is not the case. Take a look back, all the way back to the original LP. Don't forget that there are sign constraints. In the standard form, those sign constraints propagate down as x1, x2, s1, and s2, all being non-negative. So this solution that I found is actually not feasible, and therefore can't be used in the simplex method. So make sure that if you find or if you are attempting to find a basic feasible solution, that you verify that the sign of all of the variables is non-negative. My challenge to you for the homework related to this section is find all basic feasible solutions of the LP in this example. So I have found 2 of them for you already. Go through all of the other combinations of non-basic variables and identify the basic feasible solutions that appear. This covers all of the material associated to Chapter 4, Section 2.